Dear students, I welcome you to the fourth lecture of Probability and Stochastic Processes. I hope you have listened to and watched the previous three lectures carefully and you had found some interesting bits and pieces of information in those three lectures. I also hope that you have studied your class handouts and a good textbook on probability theory with good interest. And now you have a solid background in mathematical tools that we need to analyze probabilistic problems. So what we have covered in the first three lectures is that we encounter unpredictable phenomena in real life. And to analyze these unpredictable happenings, what we do, we rely on mathematics. We rely on set theory. So what we do, we look at the unpredictable phenomenon and take all its possible outcomes and put them in a set. And we call that set the sample space. The sample space could be very simple, finite, containing only very few outcomes, or it can be very complex. So far we have discussed only simple, finite sample spaces and the probabilities that we can assign to the events in that sample spaces, in those sample spaces. So you take all possible outcomes and put them in a set and call that a sample space. And then you look at subsets of the sample space. We call them events. So an event is a subset of sample space, and sample space is all possible outcomes. So we group together a few outcomes and call that an event, and we group together a few other outcomes and we call them another event. And an event can be just a single outcome. In that case, it is called a singleton. So when you assign probabilities to events, you have to be careful and mathematically precise. And your assignment should be meaningful also. All these assignments should follow the three axioms of probability and the extensions of those axioms that we can work out by following simple rules applicable to the set theory. So when I say meaningful, I mean that more likely events should be assigned higher probabilities and less likely events should be assigned lower value of probability. So when we assign probability, we are basically forming a function. So probability is nothing but a function with domain being the sigma field, and sigma field is a collection of all possible meaningful subsets of sample space. So your sigma field is your domain, and this contains all possible events, and there is a function called probability function which takes these events and assigns these events numbers, probabilities, and these probabilities should lie between 0 and 1. So probabilities are real valued numbers between 0 and 1. 0 and 1 both are included in this assignment. So the assignment should be meaningful, and less likely events should be assigned lower probability value, smaller number, and more likely events should be assigned higher probability, bigger number, but these numbers should be between 0 and 1. Why is it that more likely events are assigned higher probability and less likely events are assigned smaller probability? This should follow by simple extension of axioms of probability. I'll give you one example. Suppose that the two events that we are talking about are related to each other, that one is subset of the other. So in one event, which is the subset, there are fewer outcomes, and the one which is superset has more outcomes. So this subset is less likely event because there will be occasions when the random experiment is performed and the outcome is in this bigger set but not in the smaller set. This bigger set can be split into two sets. One is this smaller set and the other is the difference set, the outcomes which are in this set but not in the smaller set. Since this bigger set can be split into two sets which are disjoint, the probability of the bigger set is equal to the sum of the probabilities of the smaller set and the difference set. And if the difference set has a non-zero probability, then the probability of bigger set will be larger, and if the difference set has zero probability, then it will be equal to the smaller set. But in any case, the probability of more likely event will be higher. So far, we have talked about very simple sample spaces, and we have talked about assignment of probabilities to events in these sample spaces. In previous lectures, we talked about a simple sample space of a coin toss with two interesting events, head and tail, and we said since our perception is that head and tail are equally likely, we'll assign probability of 0.5 and 0.5 to the two events. So how do you actually assign probabilities if you have a real life problem like a coin toss or roll of a dice or any similar real life unpredictable phenomenon? You can use your perception, you can use mathematical and physical analysis of the problem and then come up with numbers. In previous lectures, we also talked about roll of a dice, a small cube made of plastic with small dots usually digged in the flat surface of the cube, and there are 1, 2, 3, 4, 5 or 6 dots. And we usually perceive that the dice is fair, that all these sides are equally likely to come up on the top when the dice is rolled and it comes to rest. But it's not the case, particularly for the ordinary dice which have holes digged into surface and then marked. Because of the digging of the whole symmetry of the cube is disturbed. And I told you a story about a gentleman named Willard H. Longcore, and the story is such a nice one that it should be retold. So I'll tell you again. So he had some free time on his hand, and he proposed to a professor that I'll perform this experiment where I'll roll the dice more than 1 million times. The professor accepted, and he took 80 ordinary dice, more than 80 I guess. So he took around 100 ordinary dice with digged holes on the side and rolled each dice 20,000 times and noted the outcomes. And he compiled the results with more than 1.6 million rolls of ordinary dice, and he came up with 6 numbers, and these numbers were not same. And it showed that due to the digging of holes on the side of the cube, the symmetry was disturbed and an ordinary dice is not a fair one. So how do you assign probabilities to something similar, some similar situation that you encounter in real life? I have something to show you very interesting, and let's have a look at this. I have a few geometrical figures here. They were made from cardboard and stiff chart paper, and they were made by my son, Vakas. And I'm thankful to him for making these beautiful geometric figures. So let's have a look at them. Let's look at this geometric figure first. It's a semi-cube. It is like a cube, but one dimension is smaller than the other dimension. So this surface is flatter, larger, and these 4 surfaces are smaller. So if you roll this, if you toss this, if you throw this, if you throw it up in the air and let it fall and bounce and come to rest, what do you think are the probabilities of this semi-cube turning up this way, this way, this way, or this way? As you might have guessed, it is more likely for this cube to rest either this way or that way with flat, bigger surface touching the ground compared to it landing this way. with surface with smaller area touching the ground. This is common perception. So how do you actually assign probabilities to a problem like this? If you were a physicist and you can actually come up with laws of momentum and inertia and all those center of gravities and how the center of gravity will be tilted when the semi-cube is rolling, you might come up with few numbers that reflect the non-equal probabilities of this semi-cube resting either this way or this way when it comes to rest. Another thing is, that is again our perception, that probability of this resting in this position or in this position, one of the two flat sides being up should be same because of the symmetry, unless we have digged some holes. If we have not, we have just marked A on this side and B on this side, then probability of A showing up or probability of B showing up should be same. Similarly, due to symmetry, the probabilities of these four sides, one of these four sides showing up should also be same. But these probabilities should not be equal to each other. So my guess is that this probability of this semi-cube resting this way or this way is larger than 1 over 6, and probability of this semi-cube resting this way, this way, this way, or this way is smaller than 1 over 6. So we can say probabilities of this semi-cube standing tall like this is 0.1, and probability of this semi-cube resting flatly is 0.3. So 0.3, 0.3, and 0.1 times 4, which is 0.4, 0.6 plus 0.4 equal to 1. So this is a rough way of assigning probabilities to an unpredictable real-life problem. Now imagine that this semi-cube was even thinner, and I have an example of that too here. I'll show you. Look at this. This is a very thin semi-cube. It's actually a square cross-section of a plate, a disc, square disc. So this semi-cube also can be tossed, and when you toss it, it's going to rest either this way, that way, or it's very highly unlikely, but it might rest on one of the edges. So in this case, probability of this square disc resting on bigger faces is quite high compared to this disc resting on its edge. And we can assume that the probability of this disc resting this way is say 0.48 or even 0.49, and probability of this disc resting this way is much smaller. You can take 0.48, 0.48, subtract the 2 from 1 and divide it by 4 to get the probability of that. And you can imagine if you make it even thinner, like a coin, then probability of the coin standing this way is 0, practically 0, and probability of a coin resting on one of the two flat faces is 0.5. So how do you confirm your probabilities that you assign to problems like this? One way is that you take that and toss it many times. We'll cover that in a few minutes, which is called the repeated experiment. So you take a physical model, a physical problem, and think of some probability values, assign that, make a mathematical model, and to confirm that mathematical model, you repeat that experiment many times, and using statistics, you can be sure that assignments of your probabilities was meaningful or not. Let's look at another geometric figure, and that is a pyramid. If you look at this pyramid, now it has only 5 sides, a square base and 4 triangular sides, just like the pyramids of Egypt. So if you take this small pyramid and assuming symmetry of these 4 sides and you toss it, it will either rest this way or it may rest on one of these triangular sides. So what do you think is the probability of this pyramid resting on its flat square base or resting on its one of the 4 triangular sides. You can come up with numbers and then you can confirm those numbers by taking a small pyramid and throwing it up and letting it rest many times, hundreds of times. And if you have a lot of time, like Willard H. Longcore, you can toss a pyramid like that 1,000,000 times and then come up with accurate values, more accurate values of the probabilities of small pyramid when thrown up resting on its flat base or its triangular side. One last thing. Imagine this pyramid was very tall. The base was the same, but the height was much more than this one. I do have example of 3 such pyramids, and let's have a look at these 3 pyramids. So if you look at these 3 pyramids, they have the same base area but different heights. So you can imagine what will be the probability of this tall pyramid landing on its base compared to the probability of this tall pyramid landing on its side. I hope that you can feel that this pyramid, because of its height, is not going to land very often on its base. It's going to most often tumble and land on its triangular side, this way, that way, this way, or that way, but it's highly unlikely that it's going to land on its small base, square base, very often. So you can guess that probability of this tall pyramid landing on this surface is quite close to 0.25. You can say 0.24. So if you assume this to be 0.24, due to symmetry, these 4 sides will have probabilities of 0.24, and this pyramid having a probability of landing on this flat square base will be 0.04. This intermediate height pyramid will have less probability compared to this one landing on the surface, but higher probability compared to this one landing on the flat base. And this very short pyramid will have a large probability of landing on the base and lesser probability of landing on this triangular side. Imagine this pyramid was very short, just like a coin. But because of this perturbation, still the probability of it landing on the flat base will be slightly different from 0.5. So can you imagine if you take a real coin and toss it, and you know real coins are not flat, they have engravings and writings and designs. So can you imagine the probability of a real life coin of any country being equal to 0.5? I hope you understand that it will be slightly off. It will not be exactly 0.5 unless the coin is flat on both sides, has no engravings, no etchings, and only markings written with very thin ink or any other way which does not disturb the symmetry of the coin. So if you have a real life unpredictable phenomenon and you want to assign probabilities to it, you assign them and you want to check them, you can do this by repeating the experiment many times and then collecting the results and doing statistical analysis. So what we do is called repeated experiments. So what happens in repeated experiment is that you perform the random experiment multiple times. So suppose there is a random experiment which has sample space, a finite sample space, a few outcomes. And if you perform it twice, you are observing 2 outcomes, outcome 1 and outcome 2. And if you don't want to confuse outcome 1 with outcome 2, you are looking at a vector, 2-dimensional vector. So you are looking at vector valued observations, joint observation of that random experiment, where first observation comes when the experiment is performed the first time, second observation comes when the experiment is performed the second time. And now the sample space of this repeated experiment is a Cartesian product of first sample space and second sample space, which is the same. So you are looking at sample space of pairs of observations, which is Cartesian product of the sample space of individual experiment. So what about its sigma field? Its sigma field will also have pairs, one pair for singleton type event or many pairs of observations for more complex events. So this sigma field, which is events which have pairs, is your domain, and range is once again interval 0 to 1. So if you have repeated experiments twice, 3 times, 4 times, you are dealing with vector valued observations. Your domain is a collection of subsets of a sample space whose elements are vectors, and range is once again interval 0 to 1. So this probability function is now taking domain elements from n-dimensional space and assigning a real number between 0 and 1. Take an example. The example is again coin toss. So take a coin, toss it once, observe whether head comes up or tail comes up, and then take the coin, same coin, any other coin, and toss it again. Then observe the second outcome. When you join these two experiments, you will have either head head, head tail, tail head, or tail tail. So your sample space will be Cartesian product of sample space of individual toss, 4 pairs, and its sigma field, the collection of all subsets, will be quite large, a total of 16 possible subsets of this sample space of 4 pairs. So this problem becomes slightly richer. But how do you assign probabilities to these vector valued observations? If you assume that the 2 coins or 2 tossings of the same coin are not affecting each other, if head comes up on the first toss, then it's not going to affect the outcome of the second toss. They are independent of each other. The 2 experiments are independent of each other. Then all the 4 outcomes of 2 heads, 2 tails, head tail, and tail head should be equally likely, provided that the coin is fair one. And in that case, you can say that the probability of 2 heads appearing or 2 tails appearing is equal to 0.25. Similarly, probability of head followed by tail or probability of tail followed by head is also 0.25. But if you combine these 2 events, head followed by tail and tail followed by head, and say this is a complex event where 1 head and 1 tail was observed in either sequence, head tail or tail head, then probability of this combined event will be 0.5. So if you have a fair coin and you toss it twice, then probability is higher that you should get 1 head and 1 tail in either sequence compared to probability of getting both heads and both tails, which is 0.25, and probability of getting 1 head and 1 tail is 0.5. So if you have fair coins and toss it many times, suppose 10 times, then probability of getting 5 heads and 5 tails in either order, it could be first 5 heads, then 5 tails, or head tail, head tail, head tail in alternate order, or in any order. If you combine all the outcomes where there are exactly 5 heads and 5 tails, this event will have a large probability compared to the probability of all 10 heads appearing or all 10 tails appearing. If you extend this and take a coin and toss it 64 times, then the situation is even more interesting, and the results are shown on this slide. If you look at this slide, you will see that when a coin is tossed 64 times, then the sample space is different 64-bit binary words. So there are, because you are computer science majors, so I have said it's binary word 64-bit long. So it is a collection of 64 observations, distinct observations, either 0 or 1. 0 can be tail, 1 can be head, or other way around, but the outcome of each of these 64 observations is binary, either head or tail. So the sample space is all possible 64-bit long binary words. And what are the events? They can be many. Singleton type events, complex events. For example, one event is all heads. So if you have assigned 1 to head, then all head means a 64-bit number, all ones. Similarly, all tails is a 64-bit number with all zeros. And let's look at the next event in this slide. It is one head. So what binary word does it correspond to? If you say it corresponds to 1 and then 63 zeros, you are correct. But this is not all. There are other binary words where one head appears, for example, tail, head, and then 62 tails. So there are 64 ways that you can get a head and 63 tails, where head occupies any of the 64 locations in a 64-bit binary word. Let's look at the next event. It is up to 21 heads. So if you toss the coin 64 times and 1 head, 2 head, 3 head, up to 21 heads can be grouped together and they form one event. And the last event is that number of heads that you get out of 64 tosses lies between 30 and 34. The ideal is 32. If the coin is fair, then ideal is 32, but this is unpredictable event. You cannot say that if I toss a coin 64 times, I'm going to get exactly 32 heads. Then it's not predictable anymore. Then it's not unpredictable anymore. So you can only say that if I toss a coin 64 times, then the number of heads will be close to the ideal value of 32, between 30 and 34. And we can easily find actual probabilities of all these events. And if the coin is fair, then probability of all heads or all tails comes out to be 2 raised to power minus 64, which is equal to 5.42 raised to power into 10 raised to power minus 20, which is quite a small number. And probability of other events can also be computed, and they are probability of one head is equal to 2 raised to power minus 63, which is 1.08 into 10 raised to power minus 19. And if you look at this slide, the next item is that probability of 32 heads, exactly 32 heads appearing in any sequence, any order, is close to 10%, almost 0.1. And probability of up to 21 heads is slightly less than 0.5%. So you can say the probability of either up to 21 heads or up to 21 tails appearing is less than 1%. And lastly, on this slide, you see that probability of heads being in the range of 30 to 34 is 0.447, close to half. So you can imagine if you toss this coin 100, 1,000 or even 1,000,000 times, then the probability of less likely events will be very small. And probability of more likely events, that is, that number of heads and number of tails will be close to each other, will be very high. Let's talk a little more about repeated experiments. If 2 or more experiments which are performed one after the other are related to each other in such a way that outcome of the first experiment affects the second experiment, then we have slightly difficult situation. But if the two experiments are independent of each other, then it's better, because the outcome of the first experiment does not affect the outcomes of the second experiment. Let's have a look at an experiment where the outcome of the first experiment does affect the outcomes. Actually, it affects the whole sample space of the second experiment. Suppose you have a bag which contains green and red balls. The balls are identical to each other. Suppose you have 7 green balls and 3 red balls. You close this sack, shake it a little or a lot, and then put your hand and take out one ball without looking at the ball. When you take it out and look at it, you will get either a green ball or a red ball. Since there are more green balls, 7 of them, compared to less number of red balls, which are only 3, the probability of getting a green ball is higher, and our perception tells that it should be 7/10, and probability of getting a red ball is equal to 3/10. If you observe the color of the ball and put it back, and then shake the bag again and take another ball out, then the two experiments are identical and independent, because the composition of the balls has not changed from the two occurrences of the experiment. Once again, probability of getting a green ball will be higher, equal to 0.7, and probability getting a red ball will be again 0.3. This type of repetitive experiment where the original order is restored is called with replacement. That is, you replace the ball that you took out to observe its color. And there is another variation of this experiment which is called without replacement. And it happens like this. You start with 7 green and 3 red balls, take out one ball, observe its color and discard it. And then the second experiment is conducted with one less ball, the one that was taken in the first experiment and discarded. So now the sample space has changed. The composition of the bag has changed. If the initial sample space contained 10 outcomes, they can be called green 1, green 2, green 3 up to green 7, and then red 1, red 2, red 3. And if the first outcome was a green ball and that was discarded, then the new sample space will have just 9 outcomes, green 1 to green 6, provided that we do not distinguish between green balls. Then the sample space after discarding of a green ball will be green 1 to green 6 and then red 1 to red 3. And now probability of getting a green ball is not 7/10, it is 6/9, and probability of getting a red ball is 3/9. And you can imagine if we had drawn a red ball when the experiment was conducted first time and that red ball was discarded, then probability of getting a green ball is now 7/9 and probability of getting a red ball is 2/9. So this type of experiments, repeated experiments where the outcome of the first experiment affects the outcome of the second experiment, are dependent on each other. They are called dependent experiments, but they can also be analyzed using probability theory, as we'll do in the next slide. In this slide, we assign numerical values to the outcomes of two experiments where first experiment affects the sample space of the second experiment. So suppose in the first experiment, you take out a ball and observe its color, and if all green balls are alike and all red balls are alike, then only two interesting events could be that we get a green ball, and we do not distinguish which of the 7 green balls we did get. So interesting event is you get a green ball with a probability of 7/10, and another interesting event is that you get a red ball with a probability of 3/10. Now the second experiment, actually there are two versions of the second experiment. The first version is when the outcome of the first experiment was green. Then in the second experiment, probability of getting a green ball is 6/9 and probability of getting a red ball is 3/9. And the second version of the experiment is when the first outcome was red. In that case, probability of getting a green is 7/9 and probability of getting a red is 2/9. So we can combine these two experiments and look at the combined sample space. And combined sample space again will be vector valued, which will have pairs of observations, with first entry being the color observed in the first experiment and the second entry will be the color observed in the second experiment. So when the first ball is green, then probability of getting green and again green is the multiplication of two probabilities of getting green in the first experiment and getting green in the second experiment, provided that the new sample space reflects this fact that first outcome was green. So if you can count all these things, you will see that this probability of getting green followed by green is equal to 7/10 times 6/9, it is 42/90. If you can actually look at the sample space, you will see that the sample space is Cartesian product of the sample space of the first experiment with 10 outcomes and sample space of the second experiment with 9 outcomes. There will be a total of 90 outcomes, and out of these 90, there will be 42 those outcomes where the first green will be followed by a second green. Similarly, probability of green followed by red will be 21/90. And if the first ball happens to be red, then probability of red followed by green will be again 21/90, and probability of red and again red will be 6/90. So in this slide you saw that if the repeated experiments are not independent, even then we can find the probabilities of the combined experiment by multiplying the two parts of the observation. The first part of the observation is the first experiment with a different sample space, and the second part of the observation is with a different sample space. So you don't have to take these two experiments which affect each other. You can work this out for independent experiment as well. So if you perform two experiments, dependent or independent, related or unrelated, you can still work out the probabilities of joint experiment, joint observation by multiplying the probabilities of the first observation coming from first experiment and the second observation coming from second experiment. Let's take an example. Suppose the first experiment is tossing of a coin and the second experiment is rolling of a dice. As you can see, this joint experiment has pairs of observation, with first entry being either head or tail and second entry being a number between 1 and 6. The total sample space will be 12 pairs, and you can go on and define events on this and you can find probabilities. And since these two experiments are unrelated to each other, the probability of each pair of observation will be 1/12, provided that the coin is fair and the dice is also fair. In real life, when we encounter unpredictable phenomena, and the phenomena is a cascade or repetition of unpredictable subparts, then usually they do affect each other, as it will be clear from the following interesting example. Suppose you are very good in general knowledge and you are participating in a TV game show like Nilam Ghar, and you are called up on the stage and you are asked a difficult question and you come up with the correct answer. So the host says that you have won something and it's a surprise, it's a secret. So he presents you with a small cabinet with 4 doors. And he says, behind one door there is an expensive prize and 3 other doors are empty. And you are allowed to pick a door. So you pick a door, and then the host does very interesting thing. He asks his nicely dressed assistant to go to that cabinet and open another door. He tells which door to open, and she opens that door and that is empty. So you have selected one door and the assistant has opened another door and that is empty. So prize could be anywhere behind the three doors that are still closed, the one door that you have selected and two other doors. Now the host presents you with another dilemma. He allows you to switch. By switch, he means that the door that you have selected, you can stick to your choice and say, okay, I'm going to get whatever is behind this door, or you can switch to the two doors which are still closed. What would you do? Would you switch, or would you stick with your choice of the first selection and hope for the best? It's not straightforward. But at this moment, you should appreciate that this is a cascade of random, unpredictable situations. First situation is when you are asked to pick one out of the four possible doors. And your choice is going to be random because you don't know where the gift is. So you randomly pick a door. That is first part of the experiment. Now the host, he knows where the prize is and he asks his assistant to open a door. Any door, making sure that the open door is empty. And now the second experiment is where you either stick to your first choice or switch. So these two cascaded experiments will determine if you win that mystery expensive gift or not. So what would you do? Most people that I have talked to and the students that I have taught this course, they say you should stick with your choice and hope for the best and even pray for the best outcome. But the rules of probability say that you should switch. Let's see in the slide why is it so. In this slide, the two parts of the experiments are shown and the probabilities of two parts are written. So the first experiment is where you pick a door, any door, and the probability of you picking the door behind which there is prize, there is gift, is 1/4. So the first experiment where you pick one door out of four possible doors, the probability of you putting your hand on the door which has the gift is 0.25 or 1/4. But that's just one part of the experiment. And then the second part is you either switch or you don't switch. Suppose that you don't switch. Then what happens? Then probability of you winning the prize is that you land on the door with prize behind it and stick with it. That is 1/4. Why? This probability is determined by you putting your hand on the door with prize behind it in the first part of the experiment and then not moving your hand, not switching. So the two probabilities, when you multiply them together, is 1/4. Suppose you switch. Then to get the prize, you must have landed in the first experiment on a door without a prize. And probability of that happening is 3/4. So there are 3 doors without prize and you can land on any one of them in the first part of the experiment, and probability of you landing on an empty door without a prize behind it is 3/4, and then you switch. When you switch, it's possible that you switch to a door with prize or a door without prize. Remember, we have assumed that your first choice was a door without a prize, and the assistant has opened one door which is empty. So there are 2 mystery doors remaining and one of them has prize. So probability of you landing on an empty door in the first experiment and then switching to the prize door is 3 by 4 multiplied by half. Why half? Because in the second part of the experiment, in this case, there are two doors. One of them has prize, and probability of you landing on the door with a prize is half. So the probability of you landing on empty door and then switching to get the prize is multiplication of 3 by 4 and half, which comes out to be 3 by 8, which is larger than 1 by 4. Hence, if you are good in common sense, good in general knowledge, and you happen to be on a game show where you are presented with a situation like that, you should switch. This was not intuitive, but that is how the rules of probability tell us. To summarize what we have covered today, we started with discrete probability spaces, discrete sample spaces, and extended them with repeated experiments. And there are two types of repeated experiments. One where the two parts of the experiments are independent of each other, and other where they are dependent on each other. And the probability of joint event can be found by looking at the parts of the experiment, how they affect each other, and then looking at the joint probability space. We also looked at how the repeated experiments can be used to confirm the empirical assignments of probabilities. By empirical assignments, I mean you find yourself in a real life unpredictable events and you assign probabilities to different outcomes, and then you want to test if your assignments were meaningful. So you repeat that experiment number of times, 10 times, 100 times, and if you have luxury of a lot of time, you can repeat that experiment 1,000,000 times, keep track of the observations, and use statistics to make a reasonable declaration that your assignments were meaningful or not. For that, you have to know a lot more than simple probability. You have to know statistics, the confidence of interval, and all other interesting things. So up until now, we have covered what random phenomena are and how do we analyze those random phenomena using mathematical tools, particularly set theory and its derivative ideas. So to analyze a random unpredictable phenomena, you start with sample space and you move on to sigma field, which is a collection of subsets of sample space, and then you use the concept of functions where you assign or map these events to real numbers, and those real numbers are between 0 and 1, and they are meaningful in a sense that an event which is bound to occur more often is assigned a higher number compared to an event which is less likely to occur. So we have covered simple discrete binary spaces like coin toss and simple sample spaces like roll of a dice, and other more complex but still finite and discrete sample spaces of joint experiments, repeated experiments, where the first experiment was either independent of the second experiment or it was affecting the outcome or sample space of the second experiment. All these ideas will be extended in coming lectures, where will we move to continuous valued sample spaces, where the collection of all possible outcomes will not be finite, will not be discrete, it will be uncountably infinite. And that is going to be very interesting, because then the assignment of probabilities will be very challenging and it will involve differential calculus and other advanced mathematical tools. But that knowledge can be used to solve many other more complex real life problems and many advanced scientific problems related to unpredictable experiments and unpredictable scientific investigations. Thank you.